then this your design is effective or not. For example, you have some redundant data in your database or not, or is too much information in one relation. For example, this chapter we are talking about how to make it simple and reduce the redundant data and reduce the null value inside your relation. We call normalization. Okay. So actually this chapter we're talking about information design guidelines for relational database and semantic of relational attributes, redundant information, null values in tuples, spurious tuples, and functional dependency. And after we understand the concept of functional dependencies, we use this information to normalize the relation. Actually, we have several levels of normalization. For example, we have first normalization, second normalization, and third normal. We call normal form, sorry. First normal form, second normal form, third normal form. Most of the in real world situation, actually I have heard just only about third normal form or boycott. But actually we have fourth and fifth normal form in higher level. But when you're going to higher level, your relation will have the several many of the tables of the relation, because we try to decompose it, separate it into small part of your information to be reduce the redundant data and reduce the number of null value inside the relation. So in this class we're going to talk about just only to boycott, and about the fourth and fifth maybe we can skip it. It's quite difficult to understand actually. Okay, anyway, let's try to understand the first thing, information design guidelines for relational database. So what is relational database design? Okay, we try to grouping attributes to form good relation schemas. Good is quite difficult to know, right? It's a very ambiguous one. Anyway, but it's easy to understand, like a concept of the relation, and understand how to join the table, what kind of information inside the table, for example. Two levels of relation schemas. The first one is logical, user view level, and the other one storage-based relation level. User view is actually like on the design, right? We can understand what kind of attributes, what kind of the column inside the table. But for the storage, actually is how to store the data on the hard disk and how we search for the information, for example. But we never talking about in this class. Okay, design is concerned mainly with base relations. Okay. So the problem is, what is criteria for the good base relations? So we first discuss informal guidelines for good relational design. Okay, when we're talking about the good design, we discuss formal concept of functional dependency and normal form, first, second, third normal form, and boycott is the name of the person who proposed the way to evaluate the complexity of the relation and try to reduce the complexity of them to simple one. Okay. This one is strange. This one is just normal form. Sorry about that. Relational attribute must be clear. Very simple. Guideline number 1. Informally, each tuple, each row of the data in the relation or in the table should represent one entity or relationship instance. like attributes of different entities should not be mixed in the same relation. If you have the entity employees, right? You have entity employees and you have a lot of attributes, then you transform it from ER diagram, right, to relation employees. And in the relation employees, you should store the only information of employees, not department, not the project included in the relation employees. It should be clear about the concept of the relation. Only foreign keys should be used to refer to other entities. Entity and relationship attributes should be kept apart as much as possible. Okay. The semantics of attributes should be easy to interpret. Right. Okay. So, for example, here, employee, right? Employee. If the entity employee has attribute E name, SSN, B date, address, D number. So as you can see here, all of information is just only for employee, not for department, not for project, right? Just only then. This is kind of the guideline for the good relation. Department also store the information of the department, but you can add some information for the relation to the outer table, like add the foreign key to give the information for each employee, which department they're working for. So it's when you look at this kind of the table, you can see that it's really simplified, very clear the concept, not mix up between entity. Then redundant information, interpose and update anomaly. Redundant information. If you have a lot of redundant information, you just store the same information in several tuples. So it's waste of the storage. Right? You have to pay more for the storage. And this cause problem with update anomalies. Anomalies like a mistake, error will be happen if you don't concern about the anomaly, this kind of anomaly. About the update, we have insert new data into the table, delete also one of the update, and modification anomalies. We have 3 types of anomalies for update. For example, here, consider the relation. This is not good one. Okay, update anomaly. Update anomaly. We have relation emp project. We can guess that M is employee, P project, right? Project and employee together. So we have number of employee, number of project. So we know who working on which project, right? And who belongs to which project. Okay, and we have E name. E name is the employee name, and P name is the project name. And we have number hours, how many hours the employee works on the project. So in the table, it's look maybe no problem. It's good one, very easy to understand who working on this project, right? But if we update, like changing the name of project number P1 from billing to customer accounting, okay, you change the name. Just change the name. What is happening? If 100 employees work for the P1 project, you have to change 100 roles. So it might be some problem if the program not work properly. So the data not update for all employees. You will have some problem to matching the name of the project. Okay, this is the problem of update anomaly. And about insert anomaly. Okay. Consider the previous relation M project, employee project. If we insert data, cannot insert project unless an employee is assigned to it. Like if you have a new project, just set up the new project, but not assign employee to the project yet. So if you add the data into this table, you can add just only you have information just project and project number and project name, but you don't have employee information, right? So when you add the new project, employee number, e-name and hours must be now. You cannot have any information, so it's become anomaly. And because in this table actually both of them should be together as a primary key, right? So you cannot add just only project name, project number and project name in this information. So you lost the information. Okay, and conversely, not only the project. If you have a new employee but assigned to the project yet, you cannot add employee information in this table. If you have just only one table, okay. So this one is example of insert anomaly. In previous, update anomaly. Now insert anomaly. And then delete anomaly. Okay. In the same relation, okay, what is happen when we delete the data? When a project is deleted, it will result in deleting all employees who work on the project. What is happened? If the employee works on the project only, so his information also gone, right? If you delete the project, like you delete information of all employees, and if the employees works on that project, not the other, so his information will be gone. So we don't want to do that, right? Alternatively, if employee is sole employee on the project, is only the only employee in project, deleting the employee would result in deleting the corresponding project also. If you don't have the other table, you have just only the employee and project together in one table to store employee data and project data. If you delete one of them, maybe you lost the other information also. This is a update anomaly. In update, we have insert, right? Update, insert, and delete anomaly. Okay, there are examples of anomaly. We don't want to do that. If your problem, if your data, if you're in relations, when you update the data or insert or delete, and we have this kind of problem, you have to change your table structure architecture. So, okay, this shows the schema, right? Two relation schema suffering from update anomaly. A is M department. We have information of employee here. Here is information of the employee. Employee name, SSN, birth date, address, and which department they belong to. And the other information is for department. If you use one table to store two information inside the relation, when you want to insert just only employee, this information going to be now, right? And if you add just only department information, but still not have any employees, so on the left hand side will be now. So you will have a lot of now value inside when you insert. And also if you delete some employee, and the employee just the one who belong to the department, so the department information will be gone also. So this kind of the table is not a good one. Also the project employee will suffer from the anomaly also, right? Because of this is a project number. As you can see, both of them together, SSN and P number, becomes a primary key of M project, right? If you have this, just only this table to store the information of SSN of the employee and store the project information. If you have just only this one, so the problem becomes when you have a new employee, you cannot add the project, right? So the project will be now, and the project name and information of the and information of the project should be now for all and for SSN and the name of the employee. So the other will become now. Actually, you cannot add it because the primary key should not be now, right? This is normally will be happen when you design not good. So we have to check that. Here is the example data. A lot of redundant this waste for the storage. You don't have to do that. So this shows the problem of the design, this kind of the design. And also you can see the redundant here and here also. There are a lot of redundant information because you merge two information into one table, two entity, right? Two entity into one table. Should not do that. Actually, you should just add only the foreign key. That's enough. The foreign key, that's enough. And okay, guideline 2. This guideline is about the redundant information in tuples and update anomalies. Okay, the guideline number 2: design schemas that does not suffer from the insertion, deletion, and update anomalies. Now you understand the 3 of them about the anomalies already. So please design the schema that not suffer from them. And if there are any anomalies present, then note them so that application can be made to take them into account. You have to solve them. Next is now values in tuple. Guideline number 3: relations should be designed such that the tuple will have as few now values as possible. Now, reduce the number of nouns value inside the relation. Attributes that are now frequently could be placed in separate relation. You have to separate them. If you have a lot of now, you can separate them to the other one. Reasons for now: attribute not applicable or invalid for that field of the data, or attribute value unknown, and also value not exist. Value known to exist but unavailable. Okay, unavailable. So there are a lot of reasons that the value become nouns. If you can see that the value might be a lot of nouns, so you can separate the data into the outer tables to reduce the number of nouns. Generation of spurious tuples avoid at any cost. Okay. Bad designs bad designs for a relational database may result in erroneous result for certain join operation. If you design bad design, sometimes when you separate it and then you join it back, sometimes you lost some information, or you will have more information but it's become the fake one. The lossless join, we call lossless join, property is used to guarantee meaningful result for join operation. Here is guideline number 4. Relations should be designed to satisfy the lossless join condition. No spurious tuples should be guaranteed by doing natural join of any relations. Okay, there are two important properties of decomposition. Decompose, separate, when you separate the tables, okay? And then when you join it back, sometimes you will have this kind of the problem, non-additive or losslessness of corresponding join. We try to not generate the new information. And preservation of functional dependencies. Okay, you don't know about the functional dependency yet, but okay. If you have functional dependencies, when you separate, and after that you join it back, the functional dependency should be preserved or still remain in the new relation from the join. Okay. Property A, non-additive or losslessness join. This one is extreme important and cannot be classified. If you separate the table, if you have 5 rows and you separate the table and then you join back and you get more information than 5 rows, this is a very big problem because you add information from nowhere. Okay. It's very funny, but it's become a big problem in your work. And the property B about functional dependency, sometimes it's exception. Less strength may be classified. Sometimes you will lose some functional dependency, but the data still remain completely when you join it back and not add any information into the table. Okay, this is the concept of the spurious tuples, the properties of the good design of the schema. Anyway, just the concept. So, before we talking about the normal form, we have to understand what is the functional dependencies. Okay, functional dependency. This one are used to specify formal measure of goodness of relational design, and keys are used to define normal forms for relations. Okay, are constraints that are derived from meaning and interrelationship of data attributes. So actually we have constraints and relation of attributes in a relation. So we use a functional dependency to show that relation from the key to the other attributes. So the concept is a set of attribute X. X can be one attribute or the set of attributes. Functional determines a set of attributes Y if value of X determines a unique value for Y. Okay, this is a concept of functional dependencies. And the notation here, X and this arrow Y. X determines Y. X might be a set of attributes and Y also a set of attributes. So X determines Y holds if whenever two holes have the same value for X, they must have the same value for Y. For any two tuples T1, T is tuple, T1 and T2, in any relations R, if T1x equal T2x, then T1y equal T2y. In each row at x, if x is the same, the y should be the same value. For example, if x is ID of students and y is name of student, same number ID should be represent the same name. That's all. Okay. X determine y in R specify a constraint on all relation instant R. Okay. We write as y and then we arrow to x arrow to y. Can be displayed graphically on a relation schema. Okay. Functional dependencies are derived from real-world constraints on the attributes. Here is example of functional dependency constraint. Okay, let's see. Social Security number SSN. SSN determines employee's name. So we can write here SSN and arrow and e-name, employee name. So if you have the same SSN, you should have the same name of the employee. This is meaning of the red lines here. T1x equal T2x, then T1y equal T2y. If SSN for the first tuple, T1, one tuple equal to the other one, we have two rows. Two rows. And we have set of x, right? That is the SSN. If we have same SSN, we should have the same name. This is the functional dependencies. Show SSN determine ename. And P number determines the P name and P location. Okay. The same number of the project should be represent the same name of the project and the same location of the project. As we know, the condition is one project, just one location. And here, employee SSN and project number, both of them together determines the hour per week that employee works on the project. So the left hand side become the set of attributes SSN and project number. Both of them together determine hours of work. Can be like this. Okay, this is the semantic. We have semantic, right? Meaning of this relation. How we know that? Of course, from the requirement. From the requirement in the first place that we get. And then we design ER diagram, right? Then we understand the relation of them. After that, we can separate them as functional dependencies to understand the relation between attributes. And functional dependency is a property of attributes in schema R. The constraints must hold on every relation instance R. If K is a key of R, then key functional determines all attributes in R. Because since we never have two distinct tuples that we have the same value of the key, right? Because key must be unique value for all tuples. No redundant. So when you have the information about the relation, you have to define the functional dependencies from the instance. here we try to define the functional dependency. We need to understand the meaning of the attributes involved in the relationship between them. And functional dependency is a property of attributes in the schema R. When you got the relation, a lot of columns, you have to know which one is the key, and this key determines the other one, right? If sometimes the columns or the attributes not a key, but they are like the determiner can identify the other columns, so we can also have that kind of the functional dependencies. If we back here, it's not a good one, but here SSN is the key, and this arrow from SSN, we can use SSN to determine ename, SSN determine birth date, and SSN determine the address, right? So here is the key, but D number is not the key. But when you got the D number, you can know department name. Here we call actually determiner. This also the other functional dependencies. But when we know SSN, actually we not directly know the department name, right? We have to use the D number to connect to the D name. Or this one, address. Address is not determiner. If we know the address, we don't know the other information, because this one cannot determine anything. Just the arrow point to them, to point to this address. Also here we have three functional dependencies. The first one, SSN and P number together. This is the set of determiner. Both of them can determine hours only. But only SSN in functional dependency number 2. Here SSN can determine the ename, and pname in functional dependency number 3. Here pname determines project name and location. So when you got this kind of the relation schema, at first you should identify all of the functional dependencies to understand the relation between the attributes. Which one determines which one? Okay. Now you know how to identify the functional dependencies. Okay. Understand relation property. Okay. Here, ruling out functional dependencies. Okay. Note that given state of teach relation. Okay, we have teach relation. We can say that functional dependency text determine cause may exist. Text determine cause may exist. If we know text, we know cause. If we know text Martin, we know, cause is data management. Okay, it may exist. But not for sure, because we don't have redundant text here, and we just have the small data set. But okay, it might have the relation, the text determine cause may exist. We use may. Okay. However, the functional dependency teacher determine cause, teacher determine text, and cause determine text are ruled out. Why? For example, here, if we want to identify teacher determine cause, can determine cause or not, just check Smith and Smith. If we have the same value in the determiner, we should have the same course, but here is different. So we can say that teacher cannot determine course. Okay, teacher cannot determine course. Teacher determine text. Let's see. Teacher determine text. The same. If we have the same value of the determiner Smith and Smith, we should have the same text, but here is different. So we can say that teacher cannot determine text. So what else? The other one is the course determine text. Okay, course determine text. We just check the redundant data like data management and data structures and data structures. If the same value of determiners, we should have the same value of text. But here the text is Bartram and Horowitz, so they are different. We can say that course cannot determine text. So that's all. This one not. This one not. Cannot be. This one cannot be. Just only text and course. Text determine course can be exist in this relation, but not for sure. Okay. Here, what functional dependency may exist? May exist. Okay, we have attribute A, B, C, D with extension. Okay, which functional dependency may exist in this relation? Would you please help me? A determine B is possible? No, right? Same A, different B. Cannot be. So, how about A determine C? Same A, different C. Impossible. Okay. What else? A determine D. The similar A, different D. Oh, impossible. What should we do? Okay. After that, B determine A. Okay, we have similar B, right? Different A. Impossible. Okay. B determine C. Oh, interesting. Similar C. It may exist. B determine C may exist. How about B determine D? Same B, different D. Oh, impossible. Okay, at first, you just check single attribute as the determiner. After that, what should we do? We have to add more, like a set of attributes. So, the relation change, the functional dependency change from single, and they pair together is become unique value. If this one becomes unique value, we can say that it may the good determiner. It might be a good determiner to determine everything in the table. So if both of them, it might be good to be the functional dependency like this one. A and B can determine C, and A and B can determine D. So now we can say that A and B determine C and D. This one, the set of attribute. So you can check from the data, but it's very, very difficult. It's very difficult. And we have a lot of combination of the attributes, right? So after you finish 2 attributes, you can add more to be 3 attributes as the determiner. Okay. But we don't count the self-determine. That means if A and A determine A, we cannot use that. Right? A determine A. We not count in the functional dependency. Okay. So, if I give you the example of information like this one, can you find the functional dependency yet? Okay, let's practice later. And satisfactory bad relations by breaking up their attributes into smaller relations to separate the table big one to the small one, many columns to small number of columns. And normal form conditioning using keys and functional dependencies of relation to clarify whether relation schemas in a particular normal form. Okay, actually it's like a checklist that we have to check the condition of the functional dependency. If they pass the rules of the first normal form, we can say that the relations already satisfy the first normal form. We have like a checklist. For the normal form like second, third, boycott based on key and functional dependencies of relation schema. But for the fourth normal form is based on the key and multi-value dependencies. And the fifth based on the key and joint dependencies. Is very complicated one. Actually, additional property may be need ensure good relation design. Okay, finally, when we check is the property is should we have the lossless joint dependency preservation in the final version of the normalization. Okay, practical use of normal form. Normalization is carried out in practice so that the resulting designs are of high quality and meet the desirable properties. What is that? The practical utility of these normal forms become questionable when the constraints on which they are based on hard to understand and or to detect. Anyway, when you have the table and you look at it's quite the big one, like you have a lot of columns, you have to try to check it. Do you have the redundant data? Do you have a null value? If you have a lot of redundant data and null value, you should make a hypothesis that you should normalize the table. And then you try to identify, you have to identify the functional dependencies on that table, and you can understand the complexity of the relation of the attributes. Then you can try to normalize them later. Okay. So normalization actually is try to separate the table into the small one. But we have the other keyword is denormalization. Denormalization is process to storing the join from the higher normal form relations as base relation, which is lower normal form. Why we have to do that? Actually, when you try to normalize it, you will have separate the table into the small one, and you will have a lot of tables. Sometimes it's too complex to understand at first. If it's too complex to understand, so the maintenance is become very complicated too. And the other one, when you use this kind of the table, small one, you have to join them together to retrieve the data. And when you join them all the time, you need high computing power. To reduce the computational cost, sometimes we can denormalize or join the table. Of course, you will have redundant data, but when you search for the information, it's faster. So you have to wait between the merit and demerit of the normalization. Okay. Now, these keywords of this slide is normal form, normalization, and denormalization. Now is the definitions of keys and attributes participating in keys. You can remember the keys, right? At first, a super key for a relation schema R with attribute A1, A2 to AN. It's a set of attributes S, subset of R. S is the super key, okay? It's a subset of R with the property that no two tuples T1 and T2 in any legal relation state of R will have T1S equal T2S. If S is a set of attributes, we can call the set of attributes is a super key when no any two rows of the set of attribute duplicate. For example, in the employee table here, employee table. Okay, this one is fine. Here, which one is super key? Just only SSN for T1 and T2. SSN is unique value, right? It's unique. So we can say SSN is a super key. But when SSN combination with BDET, what do you think? They are still unique. SSN with BDET, two rows of them. All of them will never duplicate because of SSN is unique. So SSN and BDET also super key. SSN and ename also super key. SSN with everything can be super key. But you must have SSN inside the set of super key because this one is unique value. The unique value combination with the other still unique, right? But if you don't have SSN in the set, we have to concern a lot. It might be unique or not. Okay, so there are a lot of super key inside the relation. Okay, this is the concept of super key. Just here is the concept. No any tuples of T1 and T2 at the set of super key attributes will duplicate. So the key is a super key with additional property that removal of any attribute of key will cause K not be super key anymore. So key is the smallest set of attribute that's still unique value. Super key can be anything, right? But the key have to be the smallest side, small side. So here in this picture, I said that SSN with the other attributes, set of the SSN with the others can be super key. There are a lot of them, but if you're talking about the key, we have to remove the additional one. So the remaining just only SSN is the smallest set. That's still unique value. So the key must be just only SSN in this table. But for employee project at B, here, the smallest set that's still unique value is 2 of them between SSN and P-name together only. If you use just only SSN, you will have a lot of duplication. Only P number is still a lot of duplication in this table. So we have to use SSN and P number combination as the smallest set that's still unique value. What else? What else? Primary key. Okay, we already talking about the key, super key. And then if relation schema has more than one key, okay. If a relation schema has more than one key, each called candidate key. Candidate key. For example, if in a student table, we have student ID and SSN. Both of them can be a key of the table. So we call both of them candidate keys. Okay. One of the candidate key is arbitrarily designed to be the primary key. You just select one of them to be the primary key. And the other, we can call them secondary key. But before you select, we call candidate keys. Okay. After select, you can call them primary key and secondary key. The other keyword is prom attribute. Prom attribute must be a member of some candidate key. If you have the combination of attributes, several attributes, combination of several attributes, one of them we can call just prom attribute. Prom attribute. And the remaining is not included in the set of the candidate key, we call non-prom attribute. So, back to this picture. Okay, here we have the SSN and P number. This one is super key. And this is smallest set. So this one also the key. And both of them is candidate key. After that, we have no choice. We have to select this one as the primary key. Okay. So SSN and P number is a super key, candidate key, and primary key. Okay. And P number we call prom attribute. And SSN, we can also call it prom attribute. And the other attribute in the table, other attributes, we call them non-prom attributes. Okay. So, for example, the other one. Here, SSN now is a super key. And SSN also a key because it's unique value, right? And then SSN is also a candidate key. After we select the primary key, SSN become the primary key. So SSN alone This one is the prim attribute, and the others are non-prim attributes. Okay, a lot of keywords. You have to take time to remember them. Okay, so from here, you're going to start talking about the normal form. So far, we understand the functional dependencies, and about the concept of the key, super key, candidate key, primary key, secondary key, and prim attribute and non-prim attribute. So we're going to use all the information to check the normalization of the table. Okay.